Right, so this is a normal chi-squared test for independence. And the null hypothesis is always the same, that the two variables are independent of each other. They should be named in the null hypothesis. In this case, gender has got nothing to do with what sort of color you like. That is the null hypothesis, and somebody has probably made a claim that it does. So if we know this data, I know I've got 90 males and 100 females, and I know that 79 in total preferred pink, 63 preferred blue, and 48 preferred red. Then the number of degrees of freedom is how much information do I have to tell you before you can fill the table in. So if I said one bit of information, 26, is that enough for you to fill the table in? Well, I could fill this one in, but I just can't fill the other bits in. So I have to give you one more bit of information. It doesn't matter which of these I give you. If I say, let's say that one, then I can immediately, sorry, make that 40. I can immediately see that that is 23. And therefore, because I know there's 90 males, I can work that out, 41 I think, and 38. So I had to say 2 bits of information. Therefore, there are 2 degrees of freedom. Now, when I put this into the calculator, so I've typed it into matrix A, and I can now run my chi-squared test. And all you do, remember, is run it. Now, technically, you should go to matrices and just check that the expecteds are all over 5. They kind of obviously will be in this case. And it says I've got 2 degrees of freedom, and it's told me the chi-squared value. Now, you know the formula for chi-squared. It is basically the sum of the differences between this table and this table. And I do that by subtracting these 2 numbers, 26 take away 22.7. I square it to get rid of all the minus signs, and then I standardize it by dividing by this number. So it's a little formula that helps me calculate the difference between these 2 tables, and I add all of that up and I get the value called chi-squared. You don't need to do it by hand ever, but it adds up to 4.5. And then the calculator works out the probability of that happening if the null hypothesis is true. So if I go back a stage, I'm here and I'm about to execute my chi-squared test. I'm just going to go down, and it says draw. So let's draw that. Now this is the chi-squared curve for 2 degrees of freedom. And it has put my chi-squared value, which was 4.52, it's here. And if I just draw it again, it'll offer me the p-value. The p-value is 10%, so this is 10.4% here. So in all different degrees of freedom 2 tables, every possible sample you could imagine that has 2 degrees of freedom have been plotted in this chi-squared curve. And we're in the top 10.4% of them. Now that is not enough to reject the null hypothesis, because if my significance level, let's say, was 10%, well, my p-value is a bit bigger than it, and so my chi-squared value just wasn't big enough. In other words, the difference between this table and the expected values, which are generated from assuming the null hypothesis is true, the difference between those 2 tables just wasn't big enough to convince me that H0 is wrong. So I have to accept the null hypothesis. Okay, let's just extend it to a slightly bigger table. Nothing really changes, but the number of degrees of freedom does. So how many are there? And remember, the formula is just the number of rows take away 1, multiplied by the number of columns take away 1. And so this is, 2 times 4, 8. I would have to tell you 8 of these numbers before you could fill in the rest, assuming you knew the totals. Okay, now that doesn't seem to make much difference. I simply go to test chi-squared 2-way. I put my matrix into A. I've typed it all in. and I run the test. I'll just run it, and I get a chi-squared value that's pretty high, but a p-value that is 11.9% this time. So I'm going to accept the null hypothesis again, and the number of degrees of freedom is 8. Now the chi-squared value is pretty high, so I was thinking, oh, the p-value is going to be small, but this is a different chi-squared curve. Every chi-squared curve is different depending on the degrees of freedom, and we can look at it. Instead of just pressing enter here, I can go down and draw it. And this is the chi-squared curve for degrees of freedom 8. So it's every possible two-way table of this size, or in fact any other one that has 8 degrees of freedom. It's all of those, an infinite number, and they're all stacked up against the expected values, and then the distance away from them is measured. Now, so what we're saying is that if the null hypothesis is true, then what is the chances that this could have happened? And of course you're going to get natural fluctuation. That's going to happen. And all of the possible samples are here. And we've measured the chi-squared distance away, and that is this number here, chi-squared, 12.7. That is 12.7 is there. And we know that that was 11 point something percent. So there's quite a lot of samples with these of this shape, with these totals. There's quite a lot of samples that would have had the same chi-squared value or worse. And so this is not enough evidence to reject the null hypothesis. Now we don't normally work with the chi-squared. I'll go to draw and I'll press P this time. 11.9%, that's the area of this bit. And it's saying 11.9% of samples, if the null hypothesis is correct, 11.9% of samples will have a distance away from the expected values like this one does, or worse. And so that is not enough evidence to reject the null hypothesis. Tricky.